So now today we are going to see the basic testings of the hypothesis, right? So if we go in the deep of that, there are first we should understand that while doing any type of test or study, there is a chance that there will be some error. So we have to find out that which type of error we are doing a lot. So that error can be either in the positive side or it can be on a negative side. What do you mean by this? Means there is a dependency of between the variables, but our study is not able to find that dependency, or there can be non-dependency and our study is saying that they are dependent. We have two variables, for example variable a and variable b, and a is not dependent on b, but our test is saying that A is dependent on B, or there can be a chance that A is dependent on B, but our test is saying that A is not dependent on B. So they are type 1 error, that is false positive. It will say yes, those factors are related, or yes, there is a significant difference between those factors, but actually it will not. And other situation can be type 2 error, that is false negative. Means there is significant difference or there is a relation between these two factors, but actually uh, but in our study our test will say that there is not. So type 1 error is the probability of finding the difference when no such difference is actually existing. I am getting the positive result and telling that factor E, for example, if I say that drug action, so drug A, action of drug A, and if I go for the action of drug B, and then what my result is saying that drug A and drug B have the difference in the efficacy. Drug B is better than drug A, but actually there is no difference. So that can be like a false positive. Means I have found the new drug, that is drug B, and I'm studying to find out that either drug B is good or not, but actually I'm getting the difference in the test, but actually it is not, no difference. And this error is permissible up to 5%, means it should not cross the 5 more than 5%. And probability of getting and probability of getting the error should be always less than 0.05, then only we can say that there is what you say that there is some good interpretation from the test. So and this 0.05 p less than 0 is also called as level of significance, and confidence is 1 minus type 1 error, that is alpha. So that is called as the confidence of the study. These are just terms which you have to remember. Type 2 error, it is the probability of inability to detect. And there is a difference. Means drug B is working. Drug B is working better than A, but in our test or in our study, it is not appearing. Right. So in that case, it is like a false negative. Right, it means our study is getting failed, but actually it is not. And this permissible limit is 20%. Fine. Here you can just see where it went here. Yeah, you see here weight is 100 gram, 100 gram, but test is showing that there is difference in the weight, right? Here 100 gram, 1 gram, there is difference, but test is not showing the difference, right? The p value, actually this p value is going to play a very major role in the study. We are going to define an hypothesis, and then we are trying to find out that either my hypothesis is correct or not. So this p value is actually going to play an important role. So it is the statistical test, and the size and can be calculated using the statistical test. It can be calculated, and what happens actually? Uh, I have drug A and I have drug B. What I do, we saw that in type 1 error there was false positive or false negative. False positive means there is no difference, but we are getting the difference, right? So in other way, if I say that which one is good for a drug action, either false type 1 error I can tolerate or type 2 error I can tolerate. In a case of drug action, which error I can tolerate? In type 1 error, there is false positive means there is no difference, but still I am getting the difference, right? In type 2 error, there is false negative means there is difference, but I'm not getting the difference. So in case of drug action, I can tolerate the type 2 error, right? Because here it is false positive, so it may, if there is no difference and if I'm getting the difference, that may be more dangerous, right? Because I can go for the drug B, right? Thinking that both are of the same both are of the B is better than A, but there is no use of that, right? In the same way, in case of false negative, there is difference, but I'm not getting this. So in this, I can think that both drugs are working fine, but actually it is not. So in case of efficacy, I can say that sorry, this one for B1 is better. But if it is regarding the side effects, then I feel type 1 error I should feel better, because here there is no side effects, but still my study will show the side effects, though. So the chance of giving the side effect to by the drug to the body is become will become least, but here it can be dangerous. Means there is a side effect, but my study will show that there is no side effects, so it can be more lethal to the patients. So which error I have to take care, that depends on which is a study or data we are handling, right? Now if I am dealing with the patient's treatment, right? If I am dealing with a patient's treatment, so in that situation also, what will happen? Either one factor is causing the problem or not. If I want to find out, so if for example a factor is causing, like smoking is has effect on asthma, actually it has effect, right? But if I get the test saying that smoking does not have any effect on asthmatic patients, So that can be more lethal. So I can't go with the type 2 error if they are giving the false negative. So in this case, but if any one factor, for example factor A is affecting the asthma, actually it is not, but if I get that factor A is affecting, so at least here there is no uh, mm, what you say that very adverse situation for the patients if I get the type 1. So I can tolerate the type 1 error, but here I can't tolerate the type 2 error. So this is going to actually depend on which type of study you are doing, what study you are doing, and that which type of error you can tolerate. Right now, p less than 0.05, p is a probability of occurrence of hypothesis. Now hypothesis we will see. I think yeah, it's there in this. Yeah, see, it will come later. So p is less than 0.05. Chances of obtaining the false difference is less than 1 in 20. So actually, how does this p work? I will just first draw here. Well, if we see that probability is 0 to 1, it will always remain in this range, where 1 is occurrence of 100% and 0 is 0%. Now, so probability will always remain in this. First, need to understand that what the probability values mean. For example, if the probability is 0.05, so what does this mean? It means actually the probability of occurrence of 5%, right? So and if it is 0.5, so that means probability of occurrence of 50%, right? So we should take care that this we should try to understand, because these terms will come again and again, these digits will come again and again. Now what happens, we give a statement in statistics. What happens, we give a statement that is called null hypothesis. Null hypothesis, we give the null hypothesis and we conduct the study and try to find out what is the probability of this null hypothesis. If the probability is less than 0.05, if it is less than 0.05, then we say that the chances of occurrence of null hypothesis is very less, and we are going to accept the alternate hypothesis, right? So but if it is more than 0.05, now this also depends on which type of study you are doing and how much error your study can tolerate. So mostly we take confidence interval of 95%. So what actually this whole term mean? It's very important to understand. It is saying that null occurrence of null hypothesis is 0.05, less than 0.05. That means occurrence of null hypothesis is less than 5%. Chances less than 5%. That means the occurrence of the alternate hypothesis is more than 95%, right? Because null hypothesis will say this will not happen. Alternate hypothesis will say opposite of that, that this will happen. So this will not happen or this will happen, the total should be always 100%. So if the occurrence of null hypothesis is less than 5%, that means the alternate should be more than 95%, right? Right, so it is clear. So if my p-value is coming less than 0.05, that is clear mean that my alternate is dominating, right? It's all so what is actually, I will just remove this. Yeah, what is actually important of this? For example, you see this, we have two drug data, drug A and drug B. By seeing this data, can you say something that either really a very significant difference is there or not? By seeing just data, it's very difficult to see, right? So what actually is there? There are tests of significance usually done to compare the difference between the group means, that is x1 mean and x2 bar mean, and variance between the SEM. We have studied the SEM. So an error of mean. The first step involved in such test is null hypothesis. Now, what is the null hypothesis? Null hypothesis is saying that, for example, if we see the smoking and asthma, smoking does not have effect on the asthmatic patient. That is the null hypothesis, and we will conduct the study to prove that the null hypothesis. What is the percentage of occurrence of null hypothesis? If it is less than 5%, that is p is less than 0.05. In that case, we are going to except the alternate one, means the occurrence of this no difference is less than 5%. So occurrence of difference is more than 5% of more than 95%, right? So and that is alternate. So we are denoting a null hypothesis by h0 and alternate by h1, right? So this is all what I told. Yeah. Now, actually, what things we are going to read for a test of the significance, how we will get the p-value, right? So there are two types of tests: a parametric test and non-parametric test. The parametric test, this type of test can be applied for the measured data, that's quantitative data, which we have already seen, right? And examples are student t-test and ANOVA. So if it is a quantitative data and which is normally distributed, it should be approximately normally distributed, it is like that, then we can go for the student t-test or ANOVA test. And non-parametric test, now this type of data is when distribution is not known regarding the parent population, and if it is not possible to make the distribution to follow the normal. In the parametric test, one thing is that the distribution should be normally distributed, right? But if it is not possible to make it a normal distribution, then we can go for the non-parametric test. And it is mostly on categorical data, like ordinal data, or you can say the nominal data. And these are chi-square test, Wilcoxon test, Mann-Whitney, Kensor-Kruskal's-Wallis test you can go. So these are the tests. These are the actually points we should remember, that in what case we can go for the parametric and in what case we can go for the non-parametric. Now t-test. This test is for t-test is student t-test. Student t-test is also called as the t-test only. Right? Introduced by Wilkins Lee Gossett, a chemist working in the Guinness. So we don't actually. A student was his pen name, so it was considered as a. Now, what was the parametric test assumption? That it should be normally distributed. So first thing is that the data should be normally distributed throughout the data set, and means it should be equally distributed towards both side of the mean, right? Now this is just a simple, well, is there any difference? who is meaner. So type t tests are three type of tests: independent one sample t test, and paired t test or unpaired t test, which is actually called as the student t test. So under the t test, this was given by the person whose pen name was student. That's why it came as a student t test. So unpaired t test is actually called as, it means if in a what you say that uh, if we just say that a student t-test, actually we are meaning the unpaired t-test. So going to see the independent one sample t-test. So in this, the formula is t is x bar minus mu naught divided by s by root n, where x bar, where this, where x bar is the sample mean. I'm getting sound of these vehicles. Where x bar is the sample mean and s is the standard deviation. So if you see that s by root, and do you remember something like from this? Anyone getting any idea what is s by root and standard deviation by root and? Think on this. This is something we have already studied, and the degree of freedom is actually I think we didn't discuss this. Df is degree of freedom is n minus 1, that is n is total number of sample you have. Now this is for the paired t-test, right? Unpaired t-test df will be different. So for a paired is useful for analyzing the data of paired sources, like before treatment, after treatment. So what will happen, the patient is same, so it is like a paired with that patient, the data is paired with that patient. So that is called that is an example of paired data set. So we are going to see here the pair t test. So in the pair, to calculate the pair t test, first thing is that we should find the difference of each pair, then calculate the mean of the difference, and then calculate the SD of the difference. So everything what we are going to work is actually on the difference, uh, right? So we'll see an example only directly. So what actually is our formula? Our formula is T equal to mean, right, x bar minus mu naught, right, x bar minus mu naught, right, and divided by, we can say SEM, right. So x bar minus mu naught divided by SEM. So first we have to find out that finish this SEM part, because SEM is containing SD, right? So SD formula is also still a headache, big headache. So to find the SD, what we did, that was summation of x minus x bar, right? SD was summation of x minus x bar divided by n minus 1, right, and whole root, and we had square of this, right? This was SD formula. So to get this first SD, what we will do, we'll find the difference between them. So here in difference we'll find, then we'll find that x minus x bar means d minus d bar. D is here 1 minus d bar is down 1.33. So 1 minus 1.33, then 1 minus 1.33, 2 minus 1.33, like that. Then we'll get d minus d bar whole square. So this value will actually be this value, After that we'll get summation of 1 minus summation of this whole. This sum will actually be the summation value of all. So this numerator I got, right? After that n minus 1, and in that way we will get this SEM, right? So SEM will be SD, whatever we will get the answer from here, SD, that SD divided by n minus 1, right? And this will give result to this answer. And above we will have T is x minus mu naught, right? So above we will get 1.33 value, and we'll calculate. We are getting T is equal to 6.30. Now this T value is not going to tell anything. We have to see this 6.30 into T table under the degree of freedom. So degree of freedom is 6 minus 1, that is 5. So in this T table, first you go for the degree of freedom 5, then you go for where your value lies. You have T 6.30. So at degree of freedom 5, 6.30 is somewhere in between this. Am I right? Somewhere in between this, somewhere will be here. Right? That means your p value is more than 0.001 but less than 0.01. That means it is also less than 0.05. That means your occurrence of null hypothesis is less than, so null hypothesis occurrence is less than 5%. That means the chances of occurrence of alternate hypothesis is more than 95%, right? So with a confidence interval of 95%, we can say that we can accept here the alternate hypothesis, right? Now see, this is the table, is the way of reporting the test. You found before the test mean plus SEM. Then you found the before the test mean, so after the test mean and SEM. Then we did between the test mean was 1.33, and this is the range. We studied that range, right? That is plus minus, maximum it can go up to this, minimum it can. So how it will get this? We will get what you say that difference. We have the mean, so adding the SEM into the mean and subtracting the SEM from the mean. If we subtract the SEM from the mean, we will get the lower value, and if we add the SEM into the mean, we will get the higher value, and reporting will be Values are mean plus minus SD for six animals. Data were analyzed by pair t test, and p is less than 0.01, right? Compared to the before treatment to the degree of freedom. Therefore, drug shows a significant analgesic effect at p less than 0.01. Means whatever difference is there, that is significant. So we are going to accept the alternate hypothesis in this case, because we got the value in between 0.01 and 0.001, which is less than actually our confidence interval of 0.05. That's the 5%, right? So null hypothesis, occurrence of null hypothesis less than 5. So we are going to accept the alternate one. Fine. So this is the reporting path. Now, if I want to move to the stress analysis for the any parametric test, we should first take care that the data is normally distributed, and that we have seen in the starting only, right? So first, our aim is to first make sure that data is distributed normally, then only we can proceed with this. That is the major thing. Fine. So for now we'll stop here.